This is the video to accompany worksheet 18.5. As with all the videos to accompany worksheets, I recommend that you work on the worksheet on your own before consulting the video. So the first question is essentially, will the aluminum act as an anode or cathode? So you need to determine, will the aluminum be releasing electrons and becoming oxidized, or will the aluminum be accepting electrons and becoming reduced? So I think the best way to do this is to set up an expression where you have E cell is equal to E cathode minus E anode, and then plug in the values that you're given to figure out whether aluminum could act as an anode or a cathode in this system. Let's start by assuming that the aluminum is going to act as a cathode. So based on the information given in the question, the overall cell voltage you want is 1.99 volts, so that would be E cell, and then we're plugging in negative 1.66 volts for E cathode, that's of the aluminum half reaction given, and then we'll solve for E anode. So if aluminum acted as the cathode, that is, it was releasing electrons, then we would need an anode with a cell voltage or half cell voltage of negative 3.65 volts. There's no such metal on our or material on our table of standard reduction potentials. So that means the aluminum cannot act as a cathode. So let's try the calculation again with the aluminum acting as an anode. So when we do the calculation with aluminum as the anode, we see that we could have a cathode potential of positive 0.33 volts. And when we look on our table of standard reduction potentials, we see that there are several metals that would fulfill that, and the one that's closest is copper. So that means our other electrode should be made out of copper, which would give us a net redox reaction of aluminum solid reacting with copper 2+ in solution to form aluminum 3+ ions plus copper solid. You'll note that this reaction is not balanced. I'm just writing out what the process actually is that's going to occur. In this redox reaction, the aluminum is getting oxidized. It's going from aluminum 0 to aluminum 3+. So it is losing electrodes. So it's acting as the anode. In the same reaction, the copper 2+ is gaining electrons. It's going from copper 2+ to copper 0, copper metal. So it's acting as the cathode. In question 3, we need to write the balanced chemical equation for the galvanic cell. To do this, we need to write the two half reactions, the reaction that occurs at the anode and the one that occurs at the cathode, and then multiply them by some number to make sure that our total number of electrons cancel, and that should balance our charge and number of species on each side. So let's start by writing the reaction of the aluminum solid being oxidized to form aluminum 3+ ions. That's a reaction that's going to happen at the anode. And then next we'll write the reaction that will happen at the cathode, where copper 2+ will be reduced into copper metal. So here are our two half reactions. We need to sum them for our net reaction and cancel the electrons. So in order to achieve this, we have 3 electrons for the top reaction, 2 for the bottom. So we need to multiply the top by 2 and multiply the bottom by 3 to give us 6 total electrons transferred in this reaction. So there's the net balanced reaction that's occurring in this galvanic cell. Question 4 asks us to draw the galvanic cell itself. So let's start by drawing 2 beakers next to each other, connected by a salt bridge. This salt bridge will contain sodium chloride And let's also draw our anode and cathodes connected by a wire. We know that the aluminum is acting as the anode, so I'm going to label that bar of metal as aluminum, and that the copper is acting as the cathode, and therefore we know that the solutions that the bars are immersed in must be the corresponding ions. So the electrons will flow from the anode to the cathode. Draw the arrow like that. And then in order to balance the charge, as in a bunch of negative charges are going to leave the anode and travel to the cathode. So we have to somehow balance those charges. So the negative charges entering the container that the cathode is immersed in need to be balanced by the positive sodium ions flowing this way in the salt bridge. Or alternatively, the electrons leaving the compartment the anode is immersed in could be balanced by chloride ions diffusing the opposite direction to balance the electrons, charge of the electrons leaving. This also gets to the question number 5. What is the purpose of the salt bridge? The purpose of the salt bridge is to balance the charge, so that as electrons flow through the circuit, you don't accumulate net charge in some location. The loss of electrons from the anode compartment is balanced by the chloride ions entering that container. For question 6, we have a new type of galvanic cell that started out under standard conditions. That means that the concentration of all the species present was 1 molar. But after 1 hour of operation, the concentration in the anode and cathode compartment is different. And our question is, what is the cell voltage? So to answer this question, we need to use the equation that allows us to calculate cell voltage under non-standard conditions. So here's the expression we need. And there are a few variables that we need to figure out before we can answer this question. First of all, what is E cell naught? That is, what was the cell voltage under standard conditions? How many electrons are transferred? That is N in the balanced net reaction. And then what is the final reaction quotient or ratio of products to reactants? So let's start by calculating E cell for this reaction. Based on the information given in the problem, we can see that zinc solid is being oxidized and iron is being reduced. So here I've written the two half reactions that are going to occur in this cell, and I've labeled them as oxidation and reduction reactions, even though I've written them both as reduction reactions. And this is consistent with the way we calculate E cell for a net redox reaction. So now let's plug these in and calculate an E cell naught value. So here's E cell naught. It's cathode minus anode. The iron is acting as a cathode because it's getting reduced in this process, whereas the zinc is acting as the anode because it's getting oxidized, giving us an overall cell voltage under standard conditions of 0.32. Now notice it's a positive cell voltage, which means it's a negative delta G, as in this is a spontaneous reaction. So let's plug this new E cell naught value that we just calculated into the equation above and calculate a Q for this particular reaction. Here's our expression relating E cell to E cell naught plus the adjustment factor based on the magnitude of Q. So I've plugged in all that information. Also notice that I've plugged in 2, a value of 2 here, because we're transferring 2 electrons in this net reaction. So now the question is, what is Q? Well, Q is the concentration of the products over the reactants. And so looking up at the reaction given to us, it looks as though zinc 2 plus would be a product and iron 2 would be a reactant. So let's plug in the information given in the problem for their concentrations. So now the concentration of the products and the reactants has been plugged into our reaction quotient expression for Q, and now all we need to do is evaluate the expression. And the final answer we get is 0.25 volts, and that answer makes sense because the galvanic cell started at standard conditions and then the reaction progressed for a certain amount of time. So that means reactants were converted into products. So after the cell has been allowed to react for a certain amount of time, you'd expect that the cell voltage would decrease, or delta G would be a less negative number because the reaction is tending towards equilibrium. In question 6, we need to construct a galvanic cell out of nickel and manganese that spontaneously generates voltage. So let's write down some half reactions that involve manganese and nickel. So here are the half reactions. Looking at the values of the reduction potentials of the half reactions, we can tell that manganese is going to act as the anode and nickel is going to act as the cathode, so that we can get a spontaneous, that is a positive, cell voltage. So now we've calculated that the cell voltage is 0.93, and that's positive because in the problem I said that it spontaneously generates voltage. So the reaction must be spontaneous. We must get a positive E cell value. The next question, question 7, is what is delta G for this reaction? So now we have to convert our E cell value to a delta G value. Here's the expression we would use. N is 2 in this problem because 2 electrons are transferred between the species when the reaction occurs. After we fill in the variables and do the calculation, we find that delta G is in fact negative, and it's 1.8 times 10 to the 5th joules approximately. Now we have to calculate the equilibrium constant for this reaction. We could do this either from the delta G value we've calculated or from an expression I gave you previously that related E cell directly to the equilibrium constant. Either one of these expressions will work. I used the first one to calculate the equilibrium constant, and I got this value. So after calculating a value for the equilibrium constant, we find that the magnitude of the equilibrium constant agrees with what we saw for delta G, as in the reaction is very spontaneous. It's a large negative number for delta G, which means that the equilibrium constant is a large number because products are highly favored, which also means that the E cell naught value, the cell voltage, is a large positive number.